Hello and welcome to Equity Education, the chemistry version. Okay, so today we're going to be looking at a chemical equilibria, and we're going to be concentrating on Kc and Kp. So I'd like you to go ahead and open up your booklets and we will get started. Okay, so chemical equilibria. We have a diagram here. So this is an example of a reversible reaction, and it's shown below on this graph. And what I'm going to do is I'm just going to write the actual equation, chemical equation here. So H2 plus I2, our sign for reversible reaction, forms HI. Now what do we have to do? We have to make sure it's balanced, so 2HI. Okay, so have a look at this graph, and I want you to have a go at explaining it. Yeah, so we'll go at filling in the missing points down here. Okay, how do we get on? Hopefully okay. So if we're going to explain this graph, we can say that the concentration, we'll start with hydrogen, decreases. So my concentration of hydrogen decreases until it reaches a constant. We can see that here. So as the reaction continues, we're going from a higher concentration to a lower concentration and then a constant concentration. For I2, we can say exactly the same. So the I2 concentration decreases until it reaches a constant, and the HI concentration increases until it reaches a constant, which isn't surprising because we're making HI. So we'll start with nothing at the beginning and eventually we'll end up with a higher concentration and a constant concentration. We can also say that dynamic equilibrium is attained when all concentrations of reactants and products are constant. So this phrase, dynamic equilibrium, if we look at the graph, it may seem that, or if we were looking at this reaction, it may seem that the reaction stopped because the concentrations aren't changing. This is not correct, so the reaction has not stopped. The reaction both forwards and backwards is continuing. It just may look from a macroscopic point of view, so if we're looking at colours or seeing things that, well, looking at things we can actually see, looks like nothing's happening, but actually the reaction is continuing forward and backwards. Okay, right, so we'll move on. Okay, so equilibrium constants. So we give the equilibrium constant the notation Kc, and I can show you how we derive the expression using a generic equilibrium equation. So my Kc equals the concentration of my products raised to the molar ratio of my products over the concentration of my reactants raised to the molar ratio. Pretty simple so far. So you can fill this out now. So the product concentrations divided by the reactant concentrations and the molar ratio. The species involved must be taken into account. The molar ratio is raised to the power of each species concentrations. Okay, so let's do an actual example now. So you've all seen this reaction before. The Haber process to produce ammonia remember we have to balance it. So 3H2, 2NH3. So my Kc expression, actually you can have a go at doing your Kc expression. So can you please fill out a Kc expression for this reaction? Okay, well, I'm sure you've all managed to do it, so we'll quickly go through it. So Kc equals the concentration of my products, which is ammonia, raised to the power of the molar ratio, over the concentration of my reactants, raised to the power of the molar ratio. Pretty simple so far. Okay, so, and as a quick aside, we're using square brackets. Remember, square brackets is the notation for concentration. So units of Kc. Again, our units of Kc are going to differ dependent on the number of reactants and products we have in our equations. But if we're going to do this example up here, it's quite easy to work out. So we can say Kc is NH3 squared. Now my units for concentration are mole dm minus 3. It's squared, so I must have 2 of them, over concentration mole dm minus 3. I have 3 of them here. I'm going to write them all out. Mole dm minus 3, mole dm minus 3 times mole dm minus 3. So this and this and this and this will cancel. And I'll have to just go down, which means I would have 1 over mole dm minus 6, mole squared to the dm minus 6, because I've times these two together here. It's over 1, so if I want to get it in 2, all on one line, I flip it round to produce mole minus 2 dm6. Again, pretty simple, but it does depend on the number of reactants and products you have in your Kc expression. Okay, so just have a practice looking at the units for different Kc expressions. Okay, now so we're going to have a go at calculating Kc in units from equilibrium concentration values. So we'll go through this together, I think. So sulfur dioxide reacts with oxygen in a reversible reaction to produce sulfur trioxide. At equilibrium, the concentrations of sulfur dioxide is 0.040 mole dm minus 3 and oxygen is 0.020 mole dm minus 3. The value of Kc is equal to 1.38 times 10 to the 4 dm cubed mole minus 1. What is the equilibrium concentration of sulfur trioxide? Well, obviously the first thing that we need to do is write the balanced equation. So we know from this that sulfur dioxide reacts with oxygen, so SO2 reacts with oxygen in a reversible reaction to produce sulfur trioxide. I need to make sure this is balanced, so 2SO2, 2SO3. Let's check the oxygens. 2 times 3 is 6, 2 times 4 is 4, plus 2, 6. My sulfurs are balanced, so I've now got the balanced chemical equation. Now I can write the Kc expression. Remember, it's the concentration of my products over the concentration of my reactants raised to the power of the molar ratio. So I now have my Kc expression. And now I need to rearrange the Kc expression to make sulfur trioxide the subject. So that means I would have SO3 squared equals Kc, I've brought this up to this side, times by SO2 squared times O2. Now all I need to do is input the values. So my value for Kc is 1.38 times 10 to the 4 times by SO2, which is 0.04 times by 0.02. If you see here, I've changed the brackets to rounded brackets, and that's because I'm doing a calculation. Yep. Okay, which gives me a value of 0.4416. So if I want to work out my concentration of SO3, it's squared here, so I need to square root it, which gives me an overall value of 0.665 mole dm minus 3. Okay, hope you followed that, and we will carry on to do another calculation. Okay, so calculating Kc in units from initial concentrations in equilibrium concentrations. Okay, so we've got a further step in this one. It's not that much more difficult, but there is a further step that you need to do at the start. Okay, so the following reaction was allowed to reach equilibrium at a high constant temperature, and we will have So here is my reversible reaction, and I'll quickly read through the question. So initially the mixture contained 0.110 mole of NO, 0.050 moles of H2, and 0.100 moles of H2O. At equilibrium, the amount of NO was found to be 0.062. The total volume of the container was 0.10 dm cubed. Determine the value of Kc for the reaction. Okay, right, so I'll give you a minute just to think about what's happening. You can write the Kc expression while you're waiting. Okay, well, I've gone and filled out the Kc expression, yeah, because we've had a lot of practice at it now. So concentration of my reactants raised to the molar ratio divide concentration of my products, over the concentration of my reactants raised to the molar ratios. Then we need to construct a table for the following values. Okay, so we need to put our reactants and our products at the top here. And we also need to make sure we put our units in here. So my initial amount in moles, my change in amount, not in moles, sorry, there, my equilibrium amount in moles, and my equilibrium concentration, surprisingly, in mole dm minus 3. Okay, so once we've got this table finished, we'll move on to the steps. So fill out all possible values in the table from the question. Okay, so simple so far. So initially the mixture contained 0.100 moles of NO. So my initial amount for NO was 0.100. My initial amount of H2 is 0.05. Do I have anything else? And 0.10 mole of H2O. Okay, and usually if you have a question like this and a value isn't given for an initial amount, it means we have 0. So I can go along and fill this out as well. Okay, so calculate the amount of NO that has reacted. Okay, so what do we mean by this? Calculate the amount of NO that has reacted. So I know that from the equation I started with 0.10 moles of NO, and at equilibrium the amount of NO was found to be 0.062. Okay, so I forgot about this. So I can fill this out as well. Therefore, to work out the amount of NO that has reacted, I need to take away my initial amount minus my equilibrium amount. So my initial amount minus my equilibrium amount, which is 0.100 minus 0.062, which gives me a value of 0.038 moles of reacted NO. Hopefully that makes sense so far. Okay, now comes the slightly trickier bit. So make sure the equilibrium algebraic equation takes into account the molar ratios. So what do I mean by this? Okay, so if we just go back up to this table, the change in amount. So the change in amount is going to be an equilibrium, an algebraic expression. Now if I look at my overall equation, I can see that I have 2 moles of NO. 2 moles of H2 produces 1 mole of N2 and 2 moles of H2O. Therefore, I can say that because 2NO has reacted, it is equal to the value of 2x. And I give my value x here as the amount of NO that has reacted. So 2x is equal to 0.038. Okay, hope that makes sense. So now you can also see that I've put little notations here for each reactant and each product. So A, B, C, D. And I'm going to fill out an algebraic expression in these boxes here so I can calculate the equilibrium amount here. So my change in amount, my algebraic expression must be my initial amount, A, minus 2x. So I've already calculated this as 0.038. H2, B, minus my molar ratio, remember, is 2 to 2. Therefore, 2x. Here, my molar ratio is 2 to 1. Therefore, remember I am making a certain amount now. So if I go back up here, 0.038 has reacted here. Therefore, I'm going to have 0.038 divided by 2 produced. So C plus X. And here there is a molar ratio of 2 to 2. So I must produce D plus 2X. Hope that makes sense. We'll just write it on the top of here to make it a bit easier to understand. So I'd already worked out that my amount of NO that has reacted was 0.038, which means because it's a molar ratio of 2 to 2, 0.038 of this must reacted, which produces 0.038 divided by 2, because there's a 2 to 1 ratio, and 0.038 here. Okay, hope that makes a bit more sense. Now I can use these, calculate the equilibrium amounts of each reactant using the algebraic expression. So B minus 2x, to look at my calculations. So B minus 2x for H2 is 0.05 minus 0.038, which gives me a value of 0.12, I have produced 0.19. So remember, this is my value for x, which gives me 0.19. And H2O, I'd already started off with 0.100, so I need to add 0.038 to it, which gives me a value of 0.138. Okay, I can now add these to my table. 0.12, 0.19, and 0.138 moles. Hope that makes sense so far. Okay, and lastly, convert equilibrium amounts into concentrations by dividing by the total volume. Well, I know the total volume is 0.1, so I can take these values and divide by 0.1, since my concentration is N over V. So it gives me concentrations of, and I'll put them in brackets, here. Okay. Okay, and input the values into the Kc expression. Okay, so lastly, I would input my values into the Kc expression. So Kc is equal to my products over my reactants, so 0.0019 for my NO over my concentration of water raised to the power of 2 over the concentration of my reactants which gives me a value of 65.4. Now I need to work out my units. So I have 1 mole dm minus 3 up here, 2 here, so that's 3 mole dm minus 3. I have 4 down here, so that would be 1 over mole dm minus 3 once I've cancelled all these out, which, flip this round, must mean my units are mole minus 1 dm cubed. Okay, so it's very similar to the first question we did, except you have to work out the equilibrium amounts from the initial amounts. I would make sure that you understand that completely. So once you've filled this out, you may want to watch this section again just for 5 minutes so you know exactly what is going on. Okay, and then we will be moving on. Okay, and our last part of Kc is the effect of a change in conditions and the value of Kc. So the equilibrium constant is unaffected by concentration, adding catalyst, and pressure. Okay, and we'll have a think about this. Actually, no, we'll just go through this to begin with. So the equilibrium constant does change when temperature is increased or decreased. Okay, so I think we need to look in this a bit more detail. So we'll do an example. So why does this happen? Let's have a look at this following example. So again, we'll use a common reversible reaction. So use the Hart process. Remember, that this delta H is the enthalpy of the reaction, and it's negative. So if it's negative, it means that the forward reaction is exothermic. So we can explain why the Kc value will change with the temperature increase or decrease by using the Chatelain's principle. I'm sure you know what this is. So as the temperature increases, the equilibrium will favour the endothermic direction. So the equilibrium in this example will favour the endothermic direction, which is the left, so it will shift to the left. Therefore, if we then write the Kc expression, we will notice something. We will notice that, fill this out, there will be a lower concentration of the products and a higher concentration of the reactants. And this is because, as we've just said, the equilibrium has shifted to the left, which means our reactants will increase in concentration, our products will decrease. So this will increase, this will decrease. Looking at our Kc expression, this number will decrease, this number will increase, which means that therefore my Kc value will decrease. Okay, so that's how we can explain how temperature can affect the value of Kc. So you need to make sure that you understand the Chatelain's principle, and you need to know whether the forward reaction is exothermic or endothermic to be able to predict the value of Kc. Right, so we'll have a quick break and then we're going to move on to partial pressures. Okay, so partial pressures. So we give the notation the Kp expression for equilibrium constant as Kp. So Kp is similar to Kc, however it deals with gaseous particles. And it's calculated in a very similar way. However, partial pressures must be taken into account. And the partial pressure can be described as the pressure a gas would exert if it were alone in a container. And the total pressure is the sum of all the partial pressures in the gas. Therefore, an expression for Kp would look like, and we'll do a generic equation again. P. So my Kp expression would be the partial pressures of my products over the partial pressures of my reactants raised to the power of the molar ratio. Okay, I hope that makes sense. So concentration has been replaced by the partial pressure of the gas. So this is the only difference in expressions of Kp and Kc. Remember, the partial pressure has been raised to the molar ratio of each reactant and product in the equation. So very similar to our Kc expression. Okay, so homogeneous gaseous equilibria. These are reactions where all the species are gaseous, unsurprisingly. E.g., we've already used this again, so we'll carry on using it. And this is a quick point. So we use this value as a Kc expression, even though it's got gases in. Occasionally this does happen, but really, if you've got gases, it should really be a Kp expression. It does depend on the exam board you're doing. Okay, so these are the reactions where all the species are gases. So if I was going to do my Kp expression, PSO3 squared over PSO2 squared and PO2. Simple. Heterogeneous gaseous equilibria. So any species that is not a gas, any species that is not a gas is removed from the equation. E.g., here I have my carbon, which is a solid, which obviously won't exert a pressure, so we can get rid of this. So my Kp expression would be partial pressures of my products over my reactants. Okay, so very similar to the Kc expression as well, and we will move on. Okay, so to be able to calculate these partial pressures, we need to understand another term, which is mole fraction. So to determine the mole fraction of the gas, we use the formula. So we use the following formula: mole fraction equals number moles of A. So I'm just taking A, which could be any reactant, over total number of moles of gas. All I'm assuming is that A is a gas, and we can use a notation for this. So for my mole fraction, I would write as XA if it was B, XB, C, XC, over my N of A, my number of moles, over my total number of moles. And we can use this mole fraction to be able to determine the partial pressure. So my partial pressure of a gas is equal to the mole fraction of that gas times by the total pressure of all gases, and I'm just going to write at equilibrium mixture. Yeah, and you will see why that's relevant in a couple of minutes. And if I'm going to write this down, I would write it as P A, so it's my partial pressure of A times by the mole fraction of A times by the total pressure. Make sense so far? Okay, so I'd like you to have a go at doing this yourself, see how you get on. Okay, right, I assume it's quite straightforward. So calculate the partial pressures of 0.3 moles of hydrogen, 0.2 moles of ammonia, and 0.1 moles of nitrogen in a container with a total pressure of 150 kPa. Okay, so the first thing I need to do is I need to work out my mole fractions. To do this, I need to use this formula up here. So my number of moles of A divided by the total number of moles of gas. So my total number of moles, let's do that first, is equal to 0.3 plus 0.2 plus 0.1, which gives me a value of 0.6. And now I can work out the partial pressures, the mole fractions and the partial pressures of each gas. So my mole fraction is my number of moles times by A divided by my total number of moles of gas, and I can put it into one formula and just times it by my overall pressure. So my partial pressure for hydrogen would be 0.3 divided by 0.6. This is my my number of moles of hydrogen over my total number of moles times by P. 150 is my total pressure. And for ammonia, 0.2 over 0.6 times by 150. And nitrogen, 0.1 over 0.6 times by 150. And these give me values of 476 kPa, 50 kPa, and finally 25 kPa. And my partial pressures should add up to 150, and I just stop for a second because they obviously don't. That's because I've written down the wrong number here. So this should be 75. So 75 plus 50 plus 25 equals 150. So I know I've got the right partial pressures for this calculation. Okay, moving on. So units of Kp are calculated in the same way as Kc, e.g. again, we'll use this example. So my Kp expression, again, I know I'm writing it a lot, but you need to get used to it. Whoops. Just about to write a Kc expression. O2. Now my units of pressure, we use this example, is kPa. Could be atmospheres, but it's usually kPa. So I would have kPa times by kPa over kPa squared. So times by kPa times by kPa. Again, these will cancel out to give me 1 over kPa, which gives me a value of k to Pa to the minus 1 if I bring it up here. Exactly the same way that we work out the units for Kc, so don't want to spend any longer on that. And we're now going to go on to calculations involving Kp. Okay, so I'll let you read it first and then we will go through it together. Okay, so calculations involving Kp. So the exact amount, the exact same methods is used for working out the amount at equilibrium in Kp expressions as Kc expressions. Partial pressures, partial pressure calculation is slightly different. And that's what you've just done previously up there. So you should be able to answer this question on your own. And again, I want you to have a go at it on your own as well. So I've left a page at the back here that you can use to fill out some notes if you'd like to. So you can either do it on a rough piece of paper or do it on the back of your notes. Okay, so have a go. Okay, alright, so how did you get on? We'll go through it. So calculating total pressure. So steam is passed over solid carbon to form hydrogen and carbon monoxide, when 3 moles of steam is heated at 700 K, the equilibrium mixture contains 2 moles of hydrogen. The Kp for this reaction is 58 kPa. Calculate the total pressure exerted in the container. Okay, so it's slightly different to your other example because you're calculating the Kc expression, but it's pretty much the same. So first of all, write down the balanced chemical equation. So steam passed over solid carbon to form hydrogen and carbon monoxide. The temperature is high, 700 K, so I know that my water is going to be a gas, and it says it in the question, H2 carbon monoxide is as well. However, my carbon is solid, it also tells me in the question. So write the Kp expression. So Kp is equal to the pressure of my products over the pressure of my reactants, apart from this one because that's a solid. That was close. And complete an initial and equilibrium amount table for the reaction. Okay, so I'm just going to write it this time because you do need to get practice at constructing them. So my initial amount in mole, my change, my equilibrium amount in mole, and obviously we don't have the concentration at the bottom because we are calculating the partial pressures. Again, I'm going to give these value as A, B and C. Okay, so what do we do first of all? Okay, so we need to complete this, and the first thing we need to do is just fill out the information in the question. So when 3 moles of steam is heated, so I know this is 3, contains 2 moles of hydrogen. Oops, sorry. Three moles is heated. Mixture contains 2 moles of hydrogen. Now that's all I know from the question. So the only thing I know is that this is 2 moles. Okay. So what does this mean? Okay, so the reason I just stopped there is because I noticed I've made a mistake in one of the values of in the question, and it'll probably become apparent by the time we get to the end. But the actual method that we're doing is exactly the same for all of these Kp calculations. So we'll leave it in, and then you'll probably notice at the end where the mistake lies. So we've drawn our table. We've put our values in. We started with 3 moles here, and we've produced 2 moles of hydrogen. Again, like we said for our Kc calculations, if we don't have an initial amount in moles, we assume that it's 0. Okay, so we can work out our algebraic expression now by saying that we know that 2 moles of hydrogen is formed from 0, so X is equal to 2 moles, and I know this because my ratio from here to here is 1 to 1. Therefore, it must mean that my change in my initial amount of A must be A minus X. This will be X, and this will be X, assuming to the molar ratios. So this gives me a value of 2, and this gives me a value of 1. Okay, moving on. So calculate the partial pressure of each gas using the mole fraction. So my partial pressure total, my total pressure, is the sum of all my partial pressures, which is my total number of moles get it right. I can add these up, so 1 plus 2 equals 5, and now I can calculate my partial pressure. So P of H2O is equal to my mole fraction, which will be 1 divided by 5, times by the total pressure, which is 58, which gives me a value of 11.6 kPa. I can work out my mole fractions and therefore my partial pressure of hydrogen, which gives me a value of 23.2 kPa, and for carbon monoxide, which will be the same, which, times by 58. Okay, so I've calculated all of my partial pressures. I can check to make sure these partial pressures are right because they should add up to the total pressure, which they do. And now all I need to do is input the values into my Kp expression. So let's just write my Kp expression for clarity again. CO over partial pressure, which gives me the values of H2, so 23.2 times by 23.2 over 11.6, which gives me a value of 46.4 P. Now I know my Kp. The Kp for the reaction is 58, so I know my Kp. So therefore, I can write my value in here, which is 58, and therefore I can work out my total pressure by dividing 58 by 46.4, which gives me a total pressure of 1.25 kPa. Okay, so you may have noticed I just said that my partial pressures add up to my kPa. Well, they don't, they add up to 58, so that's where I've made the mistake. Obviously, my partial pressures need to be higher than my kPa here. So this is the method for working it out. Although I put the wrong value in, it does still make sense. So I still hope that this is useful. Okay, so we'll go on to another calculation now. Okay, so calculating Kp. So the following equilibrium reaction was set up. I'm using this quite a lot, so we'll stick with it. Okay, and the initial amount of sulfur dioxide was found to be 2.5 moles and 3 moles of oxygen. After equilibrium was established, there was 2 moles of sulfur trioxide formed. The reaction was carried out at a temperature of 350 K and a pressure of 150 K. Right, so first thing we need to do is write the balanced chemical equation, which I've done here, and then write the Kp expression. So my Kp expression would be this, and then complete an initial and equilibrium amount table for the reaction. Okay, so I've done this for you. I want you to have a go at doing this to get some more practice, and I'll be back in a minute. Okay, hope you managed to do this. So we'll fill this out as we go through. So the initial amount of sulfur dioxide was found to be 2.5 and 3 moles of oxygen. So I can fill out my initial moles of 2.5 and 3 moles. And after equilibrium was established, there was 2 moles of sulfur trioxide formed. So 2 moles of sulfur trioxide. Well, again, we assume that the initial amount of sulfur trioxide is 0. Okay, so we know the reaction is 2 to 2 here, 2 to 2. Therefore, we can say that the molar ratio, so my change here, must be, my value of x, 2x is equal to 2, because this is my change in my initial to my equilibrium value. Okay. So that means my change here would be 2x, my change here would be a minus 2x, and the reason why this is 2x is because it's a 2 to 1 ratio here. Therefore, my change in amount of O2 would be B minus X. So I can fill this out. So 2.5 minus 2 would equal 0.5. And here 3 minus X, which would be 3 minus 1, is equal to 2. Hope that makes sense. Hope you got that as well. So calculate the partial pressure of each gas using the mole fractions. Okay, so first of all, I need to calculate my total moles. Which is equal to 0.5 plus 2 plus 2, which equals 4.5, and then I can start calculating my partial pressures. So my partial pressure for SO2 is my amount of the gas, number of moles, over my total number of moles, times by total pressure, which is 150, giving me a value of 16.7. O2 2 over 4.5 times by 150, giving me a value of 66.7. And for SO3 is 2 over 4.5 times by 150, giving me also a value of 66.7. Okay, then have a go at doing the next question and then we'll go through it quickly. Okay, so I can now input my values. I'm going to quickly just write again my Kp expression. Okay, so my partial pressure for sulfur trioxide is 66.7 squared over 16.7 squared for sulfur dioxide and 66.7 for my oxygen, which will give me a value of 0.239. Don't forget to do the units. We have 2 kPas on the top, 3 on the bottom. So again, it will be 1 over kPa leading to kPa minus 1. Okay, so hope that was helpful. Hope it made sense. Again, apologies for the second but last question. I did put a value in wrong. It will get changed eventually. But not quite at the minute. But the method is exactly the same for working out this question. Alright, okay, so hopefully I'll see you next time, and bye bye.